Hello everyone, hereby I will specifically address the knowledge about moment generating function, which is also abbreviated to MGF. Before I go to the topic, I have to describe some basic knowledge about generating function. First question is, what is moment? A moment of a random variable is just expected value of a power of the random variable. Before we go ahead, we should know what type of moment we are dealing with. In fact, there are two types in all. One is a raw moment, which is also called moment about origin. You can recognize by the formula. The formula is mu1 equals expectation of x around the variable to the power 1. By replacing k with 1, now we can get it equals to the expectation of x. Now, I will show you the formula in the following pictures. Apart from the raw moment, another is called central moment. The only difference between central moment and a raw moment is that we should distract a u, which is the mean of the distribution. Now we can see the formula as follows. We can see that the mu1 equals expectation of x minus mu power k. When the k equals 1, we can get the first moment. Now, we use expectation of x minus the expectation of mu, but we have to notice that mu here means the mean of some distribution, so we can finally get a 0 in this formula. Obviously, this means first central moment is a 0. Now, I will talk about the definition about the moment generating function. It is the expectation of x to k, which is also denoted by u subscript k, which means the kth moment of a random variable. Now let's see the picture to get a directly meaning. When we are learning moment generating function, we have to notice that the first 4 moments have special meanings respectively. The first moment means the mean of some distribution. The second moment means the variance of some distribution. The third moment means the skew of some distribution. The fourth moment means the kurtosis of some distribution. Hereby, we can easily understand that the number of k's decides which moment it is. Now, we will go to write the moment generating function for a random variable y, which is mt equals expectation of e to ty. Here is the formula. Now we have known the equation about the moment generating function. I will try to expand the e to ty for you. But when I expand it, I have to use a very complex formula, which is called Taylor's formula. I can't explain the definition of the Taylor formula in this video because of it shows totally about moment generating function. But I will still show you the Taylor polynomial and how it works in the following pictures. We replace the y with ty, then we will get what we want for the moment generating function. If you understand the theory about Taylor's formula, it will be a big help for you to understand how moment generating function come. The formulation can be explained that the expectation of e to ty is a function of all the moments about the origin. Now, we can get the very important application about moment generating function. To apply it, we have to find the derivative of mt respect to t. Although there are k entrants in the series, but we don't need to write all the derivative until k times. First, let's write the first derivative of mt to t. Then let's write the second derivative of mt respect to d. Then it's very obviously that we can write the case derivative of mt respect to d. This is because we can deduce it from the previous steps. Then set t equals 0. The result will be u subscript k. It's clearly that ye to tx is called the moment generating function. Recall that the first moment of x is expectation of x. The second moment of x is expectation of x squared. The kth moment is the expectation of x to k. Briefly, the moment generating function is the expectation of a function of the random variables. In generally, there is some difference between continuous and discrete probability distribution. The difference will be shown in the picture following. I write this equation just to remind you. Not every continuous distribution has a moment generating function. This is because not every integers can converge. Since you have known some basic knowledge about moment generating function, now I will introduce you a property about it. Consider variables y and the function u. The method of moment generating function can be used to find the probability distribution of u. Suppose u equals a plus bx. Here the a is a constant. Let's replace y with the u in moment generating function. Let's see the picture. First, we expand the series and we extract the e to ta out of the bracket. Because eta is a constant as well, then we will find the outcome as shown in the pictures. We compare the result with the moment generating function with common, discrete, and continuous random variables. If it is identical to one of these moment generating functions, then the probability distribution of u can be identified. Remember, the theory is very important and practical for you to find the probability distribution of u. For moment generating function, there is a unique series that let mxt and myt denote the moment generating function of a random variable x and y. If both moment generating functions exist and mxt equals myt for all values of t, then x and y have the same probability distribution. There is another interesting property about moment generating function. Let's suppose there is many y. Let y1, y2, yn be independent random variables with moment generating function my1t, my2t until mynt respectively. If u equals y1 plus y2 plus y3 until plus yn, then we can get the conclusion that mut equals my1t multiplies my2t multiplies my3t until we multiply it to mynt. Now, let me use an example to make you understand how useful the moment generating function is. Here is the question. I will give you a few seconds to consider it. First, I will write it in the following picture. First, let we get the first derivative of this equation. Then set the t equals to 0. Then we will get the expectation of y, that is the first moment. Now I will write the procedure step by step. You can watch how can I get the conclusion. I think it will help you to understand how it works. For question B, that is a little bit difficult than question A. This is because we can't get the outcome directly. First, we have to find the second derivative of this equation. Then still set the t equals 0. Now, the outcome we get is the expectation of x squared, which is the second moment. Then, we use the outcome to minus what we get in the question A. Or remember, it should be a power. The final result is what we want. Here I write the step to remind you what we get in the second derivative isn't the correct answer. We still have to go on. And after this step is what we needed for the solution. For question C, you don't need to do any calculate. You just have to notice that y has only 3 values. That is 1, 2, and 3. We can know this information from the given condition. So, the coefficient of the 3 entrants are the distribution of y. That is 1/6, 2/6, and 3/6. Although the question is quite easy, if you do all the 3 questions right, it shows you have basically gripped the essence of moment generating function. That is all my presentation. It is a really big challenge for me to make a presentation in second language. Thanks for your attention. Thanks.